Comes from Alexandre Ponrouch from the Institute of Materials Science of Barcelona, Spain. And he's going to speak about the parameters affecting calcium and magnesium plating and stripping kinetics. So we're looking forward to your presentation.
Thank you very much. So good morning, good afternoon, good evening for everyone attending this conference. Thank you maybe especially to the Japanese people that are maybe attending this in the middle of the night. So thanks for the organizer as well to allow us to introduce a few different cations. I've learned a lot now from the previous talks from magnesium. So I hope you will also learn, have some interesting take-home message coming from the calcium chemistry that I will introduce here. And I will try to highlight as much as possible many of the similarities that there is between these two these two cations, calcium and magnesium, as they also share many issues from the Divalent chemistry. So why calcium? So basically it's more or less the same motivation as for magnesium. So we want to work with more abundant cations and raw materials. So calcium is the fifth most abundant element on the Earth's crust. So that's much more abundant than for lithium, for instance. And of course, we do hope to be able to work safely with the metal anode. The same as for magnesium, that would allows us to bring significant improvement in terms of specific capacity on the anode side at least. And with respect to the standard potential, calcium is actually 500 millivolts below magnesium. So we also have some good prospects for assembling very high energy density cells. As I mentioned, we do share several issues with the magnesium chemistry. Most of them actually arise from the very high polarizing power of the cation. So this, of course, brings along strong Coulombic interactions with the cathode host material, so poor solid state diffusion. But it can also be problematic in the electrolytes with stronger interactions with the solvents or anions, and involves as well interfacial issues such as desolvation energy that I will try to introduce in more details in this presentation, in the second part of this presentation. So in the early 90s, the group of Professor Albach pioneered those divalent cation chemistry, mentioning that those metal anodes are strongly surface film controlled. So as soon as you get some kind of passivation layer, it tends to block the electrochemistry, blocking the divalent cation migrations through this passivation layer. And since the first generation of magnesium-based electrolyte based in linear reagents, there's been a huge improvement, mostly in terms of electrochemical stability window. So we are more over 4 volts now. And unfortunately, at the time, there was no calcium equivalent for these non-passivation film forming electrolytes. So the calcium-based chemistry was basically abandoned. A few years ago, we tried to reinvestigate a bit this domain, this research field, and we were able to assess the feasibility for calcium metal deposition, and identified one crucial parameter, which is the cation mobility within the electrolyte. So by increasing a bit the temperature, we were able to plate and strip metallic calcium. And this was done in carbonate-based solvents, so in a mixture of titanium carbonate and propylene carbonate, using calcium BF4 as the salt. And this was done on purpose to assess the feasibility of the plating and stripping in the presence of a stable passivation layer that was confirmed to be formed by means of infrared spectroscopy. and was stable upon cycling. And with these first generation electrolytes, even working at such high temperature as 100 degrees C, we were able to have an electrochemical stability window over 4 volts. So since then, several groups already started to work on this field, and several plating and stripping was reported at room temperature as well. And of course, this is still a field in its infancy. There is a lot to do still to improve this field. And in our case, we try to focus on 2 major parameters. The first one is the nature of the passivation layer. We try to pinpoint which was the conducting compound from this passivation layer. And in the second part of this presentation, I will try to discuss the impact of the solvation structure of the cation and how it can affect the plating and stripping of calcium and potentially of magnesium as well. So with respect to the passivation layer, we started this investigation by comparing 2 very similar yet very different electrolyte systems, both in ethylene carbonate and propylene carbonate mixture, but using the calcium BF4 salt or the calcium TFSI salt. And what we observed from the cyclic voltammetry performed here, you can see that basically for the calcium TFSI based electrolyte, we did not see any redox features, while we do observe some plating and stripping in the case of tetrafluoroborate anions. So to try to better understand these differences, we went to several characterization methods. So here, starting from microscopy, we used nickel particles as working electrodes, on top of which we deposited the passivation layer by polarizing these nickel particles towards negative potential value. So we reduced the electrolytes on top of these particles. And in these 2 electrolytes, and from scanning electron microscopy here, you can see already some difference in morphology for the passivation layer being formed. And from TM microscopy, what we can see is that the passivation layer formed in the calcium TFSI based electrolyte was significantly thinner and smoother than the one formed in the calcium BF4. Although this very thin passivation layer was enough to fully block the electrochemistry, so it was fully blocking. From XPS measurements, what we observe is that basically both passivation layer contains calcium fluoride and calcium carbonate. But in the case of the BF4 based electrolyte, the passivation layer was significantly richer in organic compounds and also contains borates. So we do not know yet the full, the complete chemistry of these borate compounds. But from infrared spectroscopy as well as LHG electron loss spectroscopy, what we could identify is the fact that these borates are in fact BO3 moieties, trigonal. So these are, we think now, part of the constituent of the passivation layer that allows the divalent cation mobility. So to try, of course, to assess the fact that these passivation layer chemistry is the key for achieving plating stripping, we performed this simple test. So we pre-passivated 2 stainless steel discs in calcium BF4 based electrolyte. So we formed these borate containing passivation layer on 2 stainless steel discs. that we then rinsed carefully and transferred to a BF4 or a TFSI containing passivation layer. And here you can see the new cyclic voltammogram that we obtained in these two electrolytes that we tested before. And as you can see, not only we observe calcium plating and stripping in the case of the TFSI-based electrolyte, but in this, in the presence of this pre-passivation layer, we also observed a significant increase in the calcium plating and stripping rate. So it's almost a fourfold increase in the plating stripping kinetics when compared to the BF4 based electrolyte. So there is definitely a role played by the passivation layer on the plating and stripping. So this is mandatory to have these borate and organic compounds in the passivation layers to allow plating and stripping. But it also has a strong implications on the electrolyte formulation on the plating and stripping kinetics. So before I move to the electrolyte part, I would also like to highlight one point that we already assessed as one significant point for improvement for our system is the homogeneity of these passivation layers. So here you can see infrared microspectroscopy of our passivation layer that was performed at Alba Synchrotron. And basically here what you can have is an infrared spectra that is mostly related to the borate stretching bond. So you do have an intensity, a color scale that is proportional to the amount of borates in the passivation layer. You can clearly see that these borates is not uniformly distributed on the surface. So if this is the conducting species, this is definitely something that we have to improve in order to improve the plating stripping kinetics. So moving now to the electrolytes. So we try to better understand the solvation structure of the cation, to better understand its mobility and the interfacial processes. One very useful tool for this is the RAMAN spectroscopy. So these can provide you with two very important pieces of information. The first one is the formation of contact ion pairs. So the presence of anions in the primary solvation shell of the cations that can be identified here by a shoulder or a more pronounced shoulder or a peak, depending on the amount of contact ion pair being formed next to the peak related to the anion. And the strengths of the interactions between the cation and the solvent. And here you can see the Raman spectra for TFSI-based salt using lithium, sodium, magnesium, calcium, and potassium. And as we observed and we deconvolute these spectra, we can see that actually the cation solvent and the cation anion interactions are following the polarizing power of the cation. So it is the strongest for magnesium, then for calcium, and so on. And this will, of course, have a strong implication for the desolvation energy of the cation when we want to go for plating and stripping or insertion deinsertion for the cathode material. We also identified the fact that we confirmed the fact that we have more solvent molecule in the calcium or magnesium solvation shell when compared to lithium and sodium. So we have a much more bulkier cation complex to move around in our electrolyte, which will of course be an issue in terms of mass transport in our electrolyte, which can also of course affect the overall kinetics of the process. So this in mind, we try to reinvestigate several electrolyte formulations and specifically paying attention to the impact of the salt concentration. So once again, with Raman spectroscopy here, You can see for the example given here for the calcium TFSI in ethylene carbonate based electrolyte for a solution ranging from 0.1 molar up to 1.5 molar, we can identify two major issues potentially for these electrolytes. The first one is that we start to observe contact ion pair at salt concentration as low as 0.5 molar. So we have to be careful about the formation of these contact ion pair for very low concentration, in fact. And as we have actually more solvent molecule in the solvation shell, in the primary solvation shell for this divalent cation system, we also observed a very low amount of free solvent molecule in the electrolyte for concentration as low as 1.5 molar. So we are basically entering the realm of super concentrated electrolyte for rather low salt concentration in these systems. So those are, of course, parameters to be careful about when designing new electrolyte for divalent cation-based system. So to try to quantify a bit more these issues, we deconvoluted the spectra, and we basically analyzed the results in terms of the amount of solvent molecules and of anions present in the primary solvation shell with respect to the salt concentration. So we have done that for different solvents, so dimethylformamide, ethylene carbonate, propylene carbonate, and fluoroethylene carbonate for calcium TFSI-based salt. And we made the comparison with the magnesium system for the ethylene carbonate-based solution. So here what you can see is a general trend. As you increase the salt concentration, as expected, you start to form more and more contact ion pair in the primary solvation shell. But the thing is that the threshold concentration at which you start to form these contact ion pair is strongly dependent on the solvent, the nature of the solvent, and on the donor number of the solvent. So it is actually it's more difficult to form contact ion pair with a high donor number solvent molecule. When we compare now the calcium and the magnesium system, what we can observe is, as expected from the higher polarizing power of magnesium, we start to form contact ion pair for the magnesium complex at concentration as low as 0.1 mol. So this is, of course, one thing that should be of concern when designing magnesium-based electrolyte. They are much more prone to form contact ion pair. So we expect actually that these the formation of these contact ion pair will have a significant impact on the plating and stripping kinetics. So here I'm showing the binding energies for different cation complex. So the binding energy is basically roughly proportional to the desolvation energy. That's an energy that we will have to pay before any plating or insertion event can take place. So of course, the higher this binding energy, the lower the process kinetic is expected. And here you can see that for the contact ion pair case, so the calcium TFSI complex, we have a binding energy about 4 times higher than for the complex containing a solvent molecule. So we do expect a significant negative impact of the formation of contact ion pair on the calcium plating and stripping when contact ion pair are present. And now comparing the calcium and magnesium, you can see that there is a slight increase in terms of binding energy when coming from calcium to magnesium. So now coming back to the previous results, we can start to rationalize the results we obtained previously. with the pre-passivated sample. As you might remember, the pre-passivated stainless steel cycled in TFSI-based electrolytes presented much higher plating stripping kinetics when compared to the BF4-based electrolytes. And if we look at the RAMAN spectroscopy results, here what we can observe is the fact that in the calcium TFSI based electrolytes, and for the concentration we are working at, which is here 0.45 molar, we are basically here. We do not have the formation of any contact ion pair, or at least not detectable from RAMAN spectroscopy. While in the case of calcium BF4 based electrolyte, we do already have a significant amount of contact ion pair being formed in this electrolyte. So we expect that this difference in plating stripping kinetics is at least partly associated with the difference in solvation structure in the electrolyte, in the bulk electrolyte, that impact, of course, desolvation energy and therefore the plating and stripping kinetics. And we, of course, expect that this can also play a role in the de-insertion of divalent cation in cathode materials, where desolvation, is expected to happen. So in conclusion, I hope that this mostly calcium-based presentation could be also of use for the magnesium community, as I think we are facing several similar issues. And for instance, the solvation structure of the cation within the electrolyte is one of those issues that we will have to tackle to improve mostly the overall kinetics of our system and the power performances of our system. And I'm strongly convinced that the desolvation energy will actually be a crucial parameter to work with in those two divalent cation battery chemistry to improve these power performances. So with this, I would like to conclude by the most important slide, of course, the acknowledgement of the people working in these projects. Most of the results of these presentations come from the work of my PhD students, Alfonso Saboya. I'm very grateful to the collaboration also with Chalmers University from RAMAN spectroscopy and DFT calculations, with LRCS, with Karine Davoine, for the TM and ILS spectroscopy, and for the IPREM laboratory in Pau, with Rémi Desdriver for the XPS measurements. And of course, I would like to thank the original calcium team, which was started in collaboration with Toyota Motor Europe, and Professor Rosa Palacin at ICMAD, and you for your attention. Thank you very much.
Thanks very much, Alexander. And the floor is open for discussion. Max.
Yes. Actually, I don't see any questions here, but I have some. Yeah, thank you very much. I mean, this was on calcium, but it was also on purpose because I think calcium and magnesium are very much related. There is one difference, and this is that calcium is quite big compared to the magnesium. And I wonder whether in your calculations and considerations, whether you take into account some entropy effects also. Because, I mean, it's not just about the energy. There may be an entropy effect if you have more solvent molecules in your shell that is attached or detached.
For the calculation part, we did consider similar number of solvent molecule in the solvation shell, which is not that far from the reality. In fact, we mostly see 7 to 8 solvent molecules, of course, depending on the solvents we are considering. Then for the binding energy, it's that this is only static consideration, considering the last solvent molecule present in the solvation shell. Which is actually the most relevant, I would say, because this is the last molecule, either the solvent or the anion, that you will have to strip off your cation to go for either insertion in the SCI or plating, or in the cathode material if co-intercalation is not allowed.
Okay. Yeah, it seems although calcium is kind of softer than magnesium, it still has problems to intercalate or to insert, maybe even more. Do you have any idea why this is the case?
Well, of course, then for the solid state diffusion, I'm definitely not an expert. I'm working with excellent people to try to solve the cathode issues that, and there is of course plenty of issues on this side of the battery. But yeah, well, of course, the size of the cation can be an issue. But if we only consider the size of the cation, then you can also consider the analogy with lithium and sodium. Sodium has similar size with calcium, and lithium with magnesium. And it's not only a size effect, but also a Coulombic interaction effect with the O structure. So it's a game of finding the right O structure for the right cations. And in this sense, of course, the transfer of the knowledge between magnesium and calcium is not adopted.
Yeah, I think it's not straightforward to come from calcium to magnesium and vice versa. Yeah. it's just not directly transferable. Yeah. Okay, I mean, there are also issues not only with the cathode, but also the anode. I mean, the anode is something which is, I think, even more tricky than in the magnesium case, because it's quite brittle. So it's the mechanical properties are not so friendly, I would say. And when it strips and plates, you get some black calcium dust, which can fall off, etc. So this is maybe a quite tricky thing.
Well,
so I don't see, yeah.
I would say one of the most, the main difference between magnesium and calcium on the anode side is, of course, the fact that we are 500 millivolts below magnesium. So we basically have to deal with electrolyte decomposition and passivation layer formation. Thereby, our approach to try to work with this passivation layer instead of fighting against it.
Yeah. Okay, then I thank you very much for your great contribution, and I would like to hand over to Christian for the next talk.
Yeah, thanks very much, Alexandre.